Okay, let's come back and review a little bit. So while everybody else kind of coming back, so what we can do, we can just briefly kind of review what we talked about for PCA, and then I will do a very brief part on hierarchical clustering because it's and the heat maps because that's something that we do a lot. And then Meena will take over and she will be working with the IPRG data set, right? So hopefully that will be interesting. Okay, so what we talked about so far is we work with unsupervised methods where the goal is to have class discovery, where we essentially say, go and find something with interesting variation. And PCA defines interesting variation as a lot of variance between the samples, right, for whatever reason. So in whichever gene varies between the samples, so protein, so this is the dimension which contributes to the interesting variation, right? And so the important point we made was that this variation of genes or proteins between samples may be really induced by the treatment of interest, but it may also be a technological variation or biological variation, just natural, right, for this protein. And so it may not necessarily be of interest to us, and we need to distinguish this type of sources, right? And so so 2 points. One point was that we don't necessarily find the interesting differences between the samples this way, and the second point is that things get increasingly difficult when we work with high dimensions, right? And so the example here was that if we built in 10 differences but collect data with up to 1,000 dimensions, so in the first 2 dimensions we see the differences clearly. When we increase the number of genes or proteins, suddenly our samples start overlapping because the principal components become increasingly defined by noise dimensions, right? Noise genes or noise proteins, as opposed to things which we're actually changing. And if we increase the number of features to 200 or 2,000, then our principal components are defined primarily by the noise features, right? And the interesting features which really change between the groups, they're essentially buried in this 1,000-dimensional thing. So one way I like to think about this is like when you look for a needle in a haystack. So if you made your haystack bigger, well, it's more difficult to find the needle. And so adding more and more features really sometimes creates difficulties like that. And so the good thing about mass spectrometry is that we can really work on that, right? And so we talked a lot of times already about the fact that we can have discovery workflow where we use some methods just to maybe see what is interesting, what is useful, and we can use really any method for that. But eventually we will narrow down our interest to a smaller set of targets, may follow up on these experiments with targeted methods and more biological replicates, and it would allow us to sidestep some of these difficulties, right? So increasingly with our technologies, it's not just like one-stop experiment, but it's a iterative experiment where we refine our analytes of interest more and more while increasing the number of replicates more and more. And so that's really, these are all these good reasons why it's a good strategy, right? Okay. So we looked at also at our IPRG data set, right? So we can easily see the patterns in PCA for spiked proteins if we only focus on spiked proteins. And of course, the whole thing is much more mixed up if we look at all proteins. And so one way also to diagnose that is that the first principal component, or the first 2 principal components explain like 90% of variation between the samples if we only focus on spiked proteins, but it takes a lot more principal components to get there if we have more noisy features. So that was an idea. And so the question that I had during the break was, what about scaling the measurements? So this was an example that we had where protein 1 was very variable just naturally in the organism, and protein 2 was not variable naturally in the organism, right? And so this variability kind of drove the definition of principal components. So the question was, well, scaling would mean dividing this dimension by the standard deviation, dividing this dimension by the standard deviation. And so in this particular case, it may be helpful, but what if all of this were group 1 and all of this was group 2? Then we would actually make them much more similar. So essentially, it's not very clear. So there's no single solution which works well always. And as I kind of talked to some of you during the break, my personal opinion is to not scale, but maybe what we can also do is eliminate from consideration some proteins which we know are very variable biologically, because we know that they will drive PCA. Okay, and so the last thing we talked about is that the loading, so those coefficients which multiply the individual proteins when defining principal components. So sometimes they're interpreted as important somehow biologically, but again, because the direction of the principal component explains any variation and not necessarily biologically interesting, or, variation interesting for our purposes, so it may or may not correspond to some differences between the groups. And so what we did here was to plot loadings versus p-values of comparisons of two groups for all the proteins, and we see that there is no association. But if we plot this only for the spiked proteins, then it's much more clear that proteins with high loadings are actually important, right? So again, the message here was to not necessarily interpret loadings as some kind of biologically important parameters, right? And so the summary, also kind of the discussion over the break, was that my favorite use of PCA is primarily for quality control. So before even we start normalizing the data, just to see if some samples are dramatically different from the bulk, because that most likely is due to some samples being compromised or some technological artifacts, right? So this would be a really appropriate thing. But seeing too much biology into this may be dangerous because of this difference in variation between the genes and the proteins. Okay, so this is the end of the PCA discussion. And so the last thing that I would like to talk to you about is the heat maps. And this is because probably everybody has done some of these heat maps, or certainly everybody has seen heat maps, right? And it is a very kind of ubiquitous way of displaying our data, but it's so simple, right? And it may actually be quite misleading. And so I don't mean to be exhaustive here, so I'll just highlight a few things which can affect our perception of the heat map. And if they affect our perception of the heat map, it means that they affect our conclusions from it. And it can really vary quite a bit. So for example, here, by the way, we see it right away. This was our IPRG data set. Do you see anything here at all?
There's no scale.
Well, so I just did a vanilla heat map in R, right, of this. And so, well, first of all, what are the components here? So here the columns are the samples, right? And so we see here, so that we have sample 4, sample 1, 1, 4, 3, 2, 4, 3. So even our samples don't cluster together very well, right? So the samples are the columns, and the dendrogram on top of this is the ordering of the samples by similarity in the space of proteins. And the columns are the proteins, and the proteins are ordered with this dendrogram by their similarity in the space of samples. Correct. That's exactly the point, right? So we do have some systematic structure here, but we don't quite see it because, again, it's buried into this much larger number of proteins. That's exactly the point, right? Now, can we do it better? Probably, but we need to work a little bit on different components, right? And so my point here is that, first of all, we can look at it both ways. We can think of proteins as data points, multivariate data points in the space of samples, and we can think of samples as multivariate data points in the space of proteins, right? So now, we need to think about how exactly the rows are organized and how the columns are organized. So what are the things which affect the order of rows and columns? And then the third thing is the use of color. So what does the color actually mean, and how much the difference between protein abundances it actually highlights, right? So these are all the things we need to think about. So how we structure the rows and columns, how we use the color, right? And then also, do we need all of the genes or proteins, or do we need a subset of them? So I think tomorrow we should be able to actually do some work with that. So I think for today it will be mostly Lima and D6 for hands-on, but let me just give you a preview. And so the first very important thing is the ordering. So how do we organize rows and columns? And so again, it's quite symmetric, right? So we can organize proteins in the space of samples or samples in the space of proteins. So here's a artificial example. Let's just assume that we want to look at similarity of genes, right, or proteins in the space of samples. So here I have profiles of 5 samples, and this is my 3 analytes in 3 colors. And so we want to essentially group together analytes which are similar and then kind of further apart analytes which are different. So to organize rows and columns, the first thing we need to do is to define the similarity between our profiles, right? And so you can actually see 2 things already. So Euclidean distance, which literally looks at physical proximity of data points in space, so numerically, right? So will tell us that the red and green curves are closer to each other in space than the blue curves, right? So we'll say, okay, these values are similar, these values are different. However, if we talk about proteins and mass spectrometry, so we know well that the absolute intensity of features doesn't really have any biological meaning, right? There is an ionization efficiency and things like that. So we're much more interested in profile and pattern across samples as opposed to actual numeric values of feature intensities. So from this perspective, the green line here, well, actually, the red line here is much more similar to the blue line than the green line because it has exactly the same profile across the runs. And so correlation distance will actually make the gene 1 and 2 much more similar to each other than the Euclidean distance. And so you can see the result here. So if we use Euclidean distance, we first group gene 1 and 3. If we use Pearson distance, we first group gene 1 and 2. And by the way, the height of the lines on the dendrogram reflects the extent of similarity. And so you see here, the line is somewhat higher up, so it means that they're not as similar, but here they're actually identical. Because this was a fake data set, I literally just shifted one line with respect to the other. So the definition of distance will have a quite substantial impact on the appearance of the heat map. And so sometimes so I don't think it's actually even very much documented usually, but it may have a big impact on what we see. So this is one. And so now, well, it depends on what you want to show, right? So it's actually very typical that people just use some method and say, okay, the method tells me that. It's not like that. You say, I want to look for similarity of things where, to me, similarity means this. And so then you ask yourself, what type of distance reflects my understanding of similarity, right? And so it may mean different things in different contexts, but I would argue that for mass spectrometry, we kind of want to look more at the correlation similarity because we don't care about the absolute values of abundances. On the other hand, if your y-axis was absolute quantification, you may kind of think differently, right? It depends on what you show.
I will say generally I tend to use correlation distance because I'm more concerned about what genes and proteins are correlated in similar expression profiles across samples, just knowing that lots of genes and proteins are in correlation networks that are in the same pathways.
Yeah. So, right. But again, if you were doing absolute quantification and you were looking, I don't know, at protein turnover or something like that, you may be interested in some other things, right? So, yeah, it depends. But actually, I would agree with that. So for relative quantification, we use correlation. Okay. And so, of course, the next question is, just like we had scaling and centering for PCA, we can also center and scale for the purpose of heat map, right? And so by centering and scaling now, I actually mean manipulating the numbers that go into the heat map itself, okay? And so what it means is that we now, so I actually cut the y-axis here. So now in the middle here is a 0. So this was my original plot. So centering means what? I subtract the mean abundance from the gene across all the samples. So now guess what? If I subtracted the mean, then my blue line became the same as the red line, right? So now they are identical. So now I can use Euclidean distance or correlation distance, and it will look the same as far as blue gene and red gene are concerned, right? Mm-hmm. Subtract the mean, divide by standard deviation. Okay, we work on a log scale. So same theme, right, through the whole thing, that it's much easier for us to work with divisions and additions because those have much better statistical properties than ratios. But dividing by a standard is the same as subtracting the log intensity of the standard. So yeah, but the point is that, so just saying, oh, I always use correlation distance and not Euclidean distance. Well, it depends, right? If you center your data points, then you can use Euclidean distance, right? So we have different options for that, okay? And so this is the cartoon example, right? So this is what happens with our spiking data sets, right? And so I did this original IPRG data set, didn't see much. So now if I just focus on the spiked protein, so we have this nice Latin square structure plus a couple other proteins that we added, right? And so here we have a really good kind of systematic structure between the samples. So Euclidean distance and correlation distance, well, they have some impact, but in terms of clustering of samples, I'm not sure if you can read, this is sample 333, 222, 111, 444. So now that we focused only on spiked proteins, of course we can cluster better the samples than when we had the full collection of proteins. So again, dimensionality matters, right? Even though we have clearly built-in systematic signals here, if we add more dimensions, the heat map may not be able to show that. Okay, and this is, okay, so this is centering and scaling of the data, right? And this affects essentially the orders of rows and columns. But if you work in R with the heat map, there is a option scale, which can be quite confusing because this option scale does something completely different. Because this option scale will not scale our numbers which go into the dendrograms. What it will actually do, it will scale the colors which highlight the relative importance of different abundances. And this is something, so I hope you will have a chance to practice that. So scaling actually means two things. One is scaling the data to define which rows are similar to each other and which columns are similar to each other. And the other scaling is to say, well, what color represents the highest abundance? What color represents the lowest abundance? And the reason for this scaling is that imagine you have an experiment where everything is low abundant, and then you have like one data point which is very highly abundant. It's going to dominate everything else, and then you will have like a monotone color and just one point which is very bright. So it is possible to redefine the colors in different ways. So here is, for example, what I did. I looked at the lowest value. This is some default color scheme from R. Here I took the lowest value and I set it to the lowest color and the highest values with the, so you can redefine colors and your heat maps will look very differently. So we will practice that. I just wanted to show you the impact of that. And of course, the very last piece of that is how exactly we build the dendrograms. So this is just from a book, but let me just remind you how these things work. So if we have, let's say again, we have two proteins. So this is protein 1, this is protein 2, and so these are our individual samples. So the first thing we will do, well, we define the meaning of similarity. So in Euclidean distance, it's literally the distance in this space, right? In correlation, if you have more than two proteins, it will be correlation, right? So it will look at all pairs of all samples, and it will find the pair which is the closest, and it will call it the cluster. Okay? And so now the next thing is, no, now this is a single unit. From this cluster, we will look at all pairs and find the next thing which is closest to each other. Right? And so the difference between the points is easy. How do we define the difference from a cluster to? And so now we have multiple options. So one option is to take the center of the cluster and look at the distance to the next point. We can take the closest point to this point in the cluster, or we can take, let's say here, or we can take the point which is the further away from the cluster. So at least 3 different ways. And so each of these ways defines the profile. And then, okay, so let's say this is the closest, right? So now we have a new cluster. So the next thing, again, we will look at the distance between this cloud and the next point, right? And so the way to merge the clusters and define the distance to the between the clusters or between the points clearly affects the shape of the dendrograms, and it also affects the shape of the heat maps. So I kind of started by saying, okay, in this large data set, even though we have 7 spiked proteins, we don't see a whole lot, at least on the surface. It's actually not by accident. And so the same paper that I showed before with principal component analysis also does a similar type of study for correlation. So let's say we have a correlation distance, right? So we group together the data points if they are correlated, right? And so the point they're making in this study is that the more dimensions we have, so the more proteins we quantify, the more pairs of the proteins we consider, the easier it is to find a correlation which looks high just by random chance. And so they actually illustrate that. So what they do here, they have 60 data points. Let me just draw you the picture again. And everything is completely unrelated to anything. So pure, like non-systematic, independent, random noise. So they have, these are the samples. So they have from 1 to 60, right? So 60 samples. Now, from there, they have experiment with 800, let's say, proteins and 6,400 proteins, right? So the first one is 800 and this one is 6,400. So now what they're doing is, so let's say the first dimension is something really important. Let's say it's a quantitative phenotype, something like a response to some treatment or something, right? So this is our phenotype. And then let's say that everything else are proteins, right? And remember, it's all completely independent, so no association between the individual proteins and the phenotype. So what they're doing now is they take one data set, they look at the pairwise correlations of every feature to the phenotype, and they record the highest correlation. Start over, new completely independent data set, pairwise correlations, record the highest correlation. Start over. Right? And then what they plot is the histograms of these maximum correlations which they found over many replicates. And so it is pretty clear that when you have, so the blue color is 6,400 proteins and the red color is 800 proteins. It is pretty clear that when we look hard enough, we always find something, right? So if we look at pairwise correlations between the phenotype and one of the 6,400 features, we will always have higher correlation than if we only have 800 features. And so even in terms of building the dendrograms, right, if we rely on the correlation distance or any other distance, the higher the dimensionality, the easier it is to organize our rows and columns in ways which don't really represent the biology, right? And so this is an extreme, so we don't do it in heat maps, but just since they did it. So here, they did a different example where they didn't just look at the correlation of this to the phenotype, but they look at the best 4 features in linear combination. So they have more opportunities, right? So they got whatever 6,400, choose 4 combinations of 4 proteins and see how they correlate to the phenotype. And so they report the same thing. And so you see that not only blue is always to the right from the red, but also here, I don't know if you see the numbers, the correlation here is 0.5, the correlation here is 0.7. You know, 70% correlation is something which we take seriously already, right, in many cases. There is no relationship between these things whatsoever, right? And so this is yet another argument that in high dimensions we have to kind of take things with a grain of salt. Okay, so this is all I had to say. So I was just over time from the previous part. So Meena will take over now, and I hope you will have some good experience with Lima and with DASIC.
So everyone has a flash drive for So in Flash 5, I have a P5 day 2. I will copy to my folder and let's open the R Studio. So during the 1 hour, let's practice how to use the lemma one, and then how to analyze for spectral count one. Then tomorrow in the morning we have 1.5 hour hands-on section. At that time, let's practice how to make a heat map and then PCA and so on. So here, do you like this one better, or you want to go back to the yesterday framework? Now we have a here script and the bottom is console. But yesterday we have a left-right console and then one. Which one do you prefer? Is that better? This one, okay. So I will open so this is the folder what we have today, and then I just set this directory for our working directory first. Okay, so all the results will be saved at here. And then if you click this one, the HTML one, you can see what we are gonna practice today. So just to remind, what we have. So today I also working with the ABRF data set, and especially I will use the one of the output from MSDAT. So yes, a flash drive. Do you have a flash drive? So if you remember, the MSDAT function data process main goal for this function is make a protein level summarized values. So for lemma, we need the one specific protein value per each run. So that's why we just want to get this one from MSDAT. So after this, yesterday we practiced how to make a group comparison. Inside of the MSDAT, we used the linear mixed model to consider group and subject and time course. But instead of this part, we will use the lemma function, okay? And just to remind, from here, we have a run level quantification value. And if you have a run quantification value, if they have a technical replicate, this quantification function, what we practiced really at the end of the hands-on section yesterday, we can get a sample quantification value. And this output can use for heat map and the PCA and so on, okay? For both cases, we need the output from this data processing function, which already consider missing value and outlier and so on. So let's start to do this. So first, let's try to load lemma. It should be installed in your computer when you install the MSDAT. So I will click run. Here the lemma is there, and then also we need to call the reshaped2 function because we somehow need to reformatting our data set. So I will run this. So lemma and then reshaped2 function, the package is ready to use it. Okay. And then if you go back to one of the folder, data skyline, I already put the quant skyline data set, which is the output from the data processing. Okay, so we need to call this data set. So let's run this, and now we have quant skyline data here. Okay. Just to review what kind of information they have. So I can type names, quant, skyline, there are 5 different data heads. The process data have original intensity and then log to transform and then normalize intensity, which we will use for protein quantification. And then run level quantification data have the run level summarized values. So that data set we are going to use for next analysis. So I will get only the run level data set. So I will make this one is input. Then let's check the how input look like. So here we go. So input data have run information, and for each run, for each specific protein, log intensity column have a summarized value. Other one is just for just additional value, but we will use this specific 3 columns. Okay. So far, what we are doing is just read the output from data processing function to get the run level intensity. And MSDAT output, they have a long format, right? Each row have one specific run intensity values. But for lemma, we need to make a table. Means each row should be protein ID, and each column should be run value. So all between the column and row, everything should be the numbers, the protein intensity values. So, sorry? Oh, so here, the MSDAT output, we have a long format, which means each row is for run and the proteins, and each run have only one specific intensity, right? But lemma need the kind of matrix. So each row have to be protein, but each column have to be run. So inside of that one, everything should be the numbers, protein intensity. So here, that's why I use the dcast function in the reshape, just changed long format to wide format. Okay. So I just said from input data set, always left should be row, and then the other right should be column. Okay, so row have to be protein information. Column should have the original run information. And inside, we will put the log to intensity from this input data set. Okay. I run this line, and then I call this is input wide. And when I check this data set, here, each row have a protein, and then column have a run ID, right? Yes. Oh, so this is from HTML file. I just copy all the code part. I will put this one, only R script, I will put in the GitHub later. Oh, in the flash drive? In our, did you get the flash drive? Yeah, no, today. We have another one, yes, yeah. So everyone got this input wide format? Yes? Right? But here still first column for this input wide have a protein ID, so character one. So we want to put this one to the row name and then want to remove this specific columns. So I just make a row name for this protein ID. Then let's check how it look like. So here they have a row name with the protein, but they still have a protein columns, the first columns, right? So I just want to remove this first column with the protein ID. So here, from the input wide, I will subtract the first column, -1, okay? Then when I run, when I just double check, here now I don't have the protein column anymore, but I have a protein ID for in the row name for this data set. Okay, so what I did so far, read the protein quantification value and then just reformat it to the wide format. Okay, so just a little bit data manipulation. Okay, and to make a group comparison, do you remember when we do group comparison function yesterday, we need to set the comparison matrix, which comparison do you do I want? So this is also we needed. We need to set how many group information over there for each run, each column, and then which comparison I want. Okay, so here there are several functions to make easy in the lemma. So first, I want to make the matrix for this model, and then the factor will be 1, 2, 1, 1, 1, 3, 2, 2, 2, 3, 3, 3, and 4, 4, 4. So let's try to run, and then let's see how the design look like. Okay, so here we go. This is quite, they made some metrics, right, based on this information, and then they set each one is for which condition information. I just set it, and if you look at this one, now here is our design. So each row is exactly for column annotation from wide format, and then for each row it says which condition information they have. Okay, so this design tell experimental design for this specific experiment. Okay, so this is basically allow each run have which group information they have. Okay, we are not saying exactly what comparison we want. We just say the specific run, first run have condition 1, second run have a condition 2, and so on. Okay, then make contrast function in the lemma says, so what I want. So we already set the column name. So if you want to condition 2 minus condition 1, you can just easily type it, condition 2 minus condition 1. Okay, now yesterday we practiced 6 possible paired comparison, but let's try the first 3 ones. So I want to compare condition 2 minus 1, 3 minus 1, 4 minus 1. So you need to just list what comparison do you want. However, you need to mention, so what is this design look like for this specific experiment. So we need to mention what kind of the design for we have. Okay, so I will run this, and then what is this contrast matrix look like? So each level they have 4 different group, and I want 1, 2, 3 comparison. How you assign this constant is the same as what we practiced yesterday. Okay, so 2, 1 minus condition 1, and so on. Okay, then what we do so far, we made the wide format data, and we made the contrast matrix. Then we are ready to compare the groups. Okay. So first, this is the main hypothesizing part. First, function, we have to do L and fit. F should be capital. This is our data set, and then this is our experiment design. Let's fit the linear model first. Just fit the model, okay? So if you run fit this, and then first we can check what kind of the output they have. Just check the class. They specifically they have a different, like not data frame, not vector or and so on. They have own class. And then if you check name, it shows what kind of output we have. There are quite a lot of the output included. So for example, here it shows the coefficient for each group after we feeding the model, and then variance component, degree of freedom, and so on. So quite a lot of information. So we feed the model first. Then among what we feed, we need to say, so I want this specific comparison. This specific comparison. So here we can use contrast.fit functions, but we have to put the fitted model, and then we need to say what kind of specific comparison we needed. Okay. So it's done. Then let's check how the fit 2 look like. They also have a lot of the information there already. They just here, for example, here they have a variance component between this one, and then they already calculate the coefficient, means, estimate the log for changes, and so on. This is the basically linear model, but after that, this is the main part. We can calculate the moderate, the t-test, and so on. What Olga explained. Yes.
I'm actually getting an error message when I try and run the fit.
Mm-hmm.
It says error in lim fit, row dimension of design doesn't match column dimension of data object.
I see. So probably this part. Yes. So maybe probably this part when we assign the this matrix. Mm-hmm. That is my guess. Yeah. I will come back after go through this one first. So E-based function calculate the moderate t-test, what we learned during the lectures. So let's run this, and if you check what kind of the output this fit3 have, they have even more, like 12 different data set. For example, here they have a p-value, and then they have f-value, and even f, p-value, and so on. There are quite a lot of information they included. Okay, so this is done, but I want to subtract what actually we needed, and then based on information, I will use MSDEV volcano plot function to make the same volcano plot. Okay, so for basically lemma 1, just to summarize, make a wide format, set the matrix, and then set what kind of comparison do you want, and basically 3 line, fit the model, and then compares, and then you can calculate the moderate, the test statistics, and pretty much this is done. But after one is just I want to a little bit manipulate to make a different format of the output, because this one is, for example, let's see the fit3 coefficient. Fit3 coefficient, they have this matrix include only coefficient 1, right? But we want to know for a specific protein, for a specific comparison, what is the estimate for changes and p-value and so on. So I want to make a more the long format as what one of the output from the MSDEV one. So that's why I will just reformat it a little bit. So here, dcast make long format to wide format. Mel function make wide format to long format. Okay, So here, if I melt this coefficient 1, and let's check the first 6 rows. It shows for each row have a protein name and then what kind of comparison, and then here is the log to estimate for changes, right? Then here column name, they said just variable 1, but I want to change this column name to know what actually we have. So I want to first, if you run column name, this one, it says the variable 1, contrast, and p-value, but I want to change this one for proteins, label, and log2 for changes. As same, the column name is MSDAT output. So I just change the column name. Then after I just go back to head, then now we can see this format. It's getting similar to MSDAT output.
Why don't you just call top table?
The top table, we can call that one, but there was some issues, what I remember. Yes, the top table can calculate advanced p-value.
Yeah, so when you call top table, it automatically compiles
by the order, right?
Yeah, and you
Yeah.
specify a contrast by name or by number in your.
Yes. Is it also possible combine all the coefficient p-value and adjust p-value?
Yeah, so if you specify multiple fits, it'll give you an f-test for all those coefficients.
Yes.
Or if you want to do for each coefficient, you can apply top table across your list of contrast, and then you'll get one giant table for everything.
Okay, so I will haven't test that one, but yeah, maybe we can. Maybe I will dig in. Yeah.
The thing to consider is top table. There's old top table and new top table. Old top table has a lowercase t in table. New top table has an uppercase t.
Okay.
Sort of like how there's two lim fits.
Okay.
The lowercase is the older version.
I see.
That
Yeah.
can sometimes throw errors.
I see. Okay. So this is how I just made it. Yeah. So here I got the coefficient 1, and then I got the p-value table again from the p table. So same thing. Look at here. They have a p-value and construct, and then proteins. And then I just change the column name here. And then now we have a 2 table for log2 for changes and p-value. So I just merge these 2. So merge these 2 table by same name of the protein and then same name of the labels. Right? So they just find a unique protein and then label, and then they have a 2 different value for other column. They just put the different column in the one tables. So when I run, now we have these tables. So now we have estimate for changes and p-value, but we also want to calculate the adjusted p-values. So we are the next section, we are talking about the different type of adjusted p-value and then how it's going to be affected. We also have some hands-on section, but let's hear the Benjamin-Hochman one is most common one and then default option for adjusted p-value. So I will practice how to I will use this method for adjust p-values. So this 2 line is calculate the adjust p-value by different comparisons. So here means I want to separate this p-value by label. The label is different comparison. Then among them, I just want to apply the Benjamin-Hochman adjust p-value one. So after I apply, now I have this wide format one. So I just also a little bit changes. First, I just put here there's no protein names. I just put the protein name at the row columns, no row, and then make this is long format. And then here's a similar as well we saw. Then I just change the column name. And also same things. So merge with our previous data set. Now we have this tables. So the reason I make this the same name, because if you have a unique the same column name, definitely we can use this one from the volcano plot function in the MSDES. So that's why I just use the same protein and label and log2 for changes and so on. So this is the result with the same protein quantification but with a different testing strategy. So I will save this one under data skyline folder. Then under the data skyline folder, you already have a test remark result, the R file or CSV files. Okay. Then let's try to draw the volcano plot. Definitely you can use the ggplot one, but I just want to compare what we did yesterday. So I just want to use the same format. So first we need to call the MSDAT function. And MSDAT, after group comparison, they have some extra columns. So issue column is what I briefly mentioned. If they have one condition is completely missing or something, they have a value. But actually inside of that function, they check this specific issue column. But now we don't have it, so I just make a new column, but I just put the NA value, just make it working in the group comparison plot. So here, after I run it, this one is exactly same, but I just put extra one column to make it work. Then use the same group comparison plot. Then in this folder, now we have the PDF files for 3 comparisons. So then let's try to look at how it's different. So the desktop in the folder what I have, now I have this volcano plot with the lemma. Okay. If you go back to the previous folder, what we practiced yesterday, at the backup, at the data skyline, we already have volcano plot, go through everything from the MSDAT. Here it is. So here is condition 2.1, and here is the condition 2.1. Now we can see 1, 2, 3, 4, 5, 6, and then here 1, 2, 3, 4, 5, 6. And it look at each position. Actually, they have a same proteins. It's quite similar result, even with the same cutoff. Let's go through the other one. Look, This one also quite different, but here is a little bit one slightly different one. This is not spiking one. This is a false positive one, the background proteins. And then here, condition 4 and 1. Here also 1, 2, 3, 4, 5. This is really quite similar, that one, right? So in this case, the lemma and then the linear model in MSTED, even though they have only three samples per each group, they don't have much difference in these cases. So if go back to the one of the slide, what Olga mentioned this morning, this is one of the examples. So what we practice is exactly this one. So we use the run summarization from MSTED, but we use the different testing strategy here. So here and here, this one is really quite similar, right? However, even this each column, if you want to compare between row, they show different summarizing method, how actually it will be different. For example, here we use the same linear model, but different summarized method is quite different result. We can find this, a lot of the false positive here. Even we use the same lemma, if you use the different summarization method, their result also quite different, right? Before we get the data, if you go through the different protein identification and different methods for quantification, absolutely data is different. For example, Skyline, Progenesis, Maxcon, we have a different input. Even though we start the same input, each step depending on your decision. Also, so very one step, if they have a different decision, also you can get a different result for this part. Is it okay so far?
How does this change with biological replicates? So we're just using technical replicates.
Yes,
right?
yes.
So how does it change with biological replicates?
So if you have a different annotation, when you define the annotation table, each run, biological replicate and condition, you can change this biological replicate. So for example, in this case, in this experiment, for condition 1, 3 different run ID, but we have a same biological replication ID, right? But if we have a 3 different biological replicate, 3 different run ID, 3 different biological replicate ID, but from the same group, right? In model itself, what we can change in the MSTED, if you don't have technical replicate, if you have only biological replicate within each group, actually we assume we cannot distinguish like subject variance because we don't have much degree of freedom. So that very biological variance, we assume that is just general the error variance. However, if you have biological replicate and technical replicate for within the biological replicate, we can distinguish group difference and subject difference, and leftover one is really error terms. So in the cases, we can subtract the biological replicate effect. Is it okay so far? So actually, I just put the one challenging over there. So if you want to, now we make the 3 comparison, 2, 1, 3, 1, 4, 1. If you want the other rest of the comparison do you want, you can change this matrix contrast. What compares do you want? If you just change this part and go through again, you will get the rest of the comparison result. So the goal, what I showed this one, if you have some limitation to use linear mixed model in the MSTED, you can get the protein quantification because it doesn't matter about your experiment design, because we never use group or biological replicate information for protein quantification level. We only consider features and the run information. So you can get that protein quantification one, and then you can just use lemma or the method for testing one. Okay, so this is just a basic script, but you can find there are tons of sources how to use this lemma, and then tons of options. Yesterday I searching that manual is 150 pages for only lemma, the manual. So that is the one simple workthrough. And in HTML file, I already put how you can compare the older result from lemma versus the MS-1. You can just apply some threshold for adjust p-value and then get some subtract. And then you can make a diagram or you can count and so on. So this is just practice, but we can talk about this one is later, or you can go over because we have only 20 minutes left. And I will just go over, briefly also go over how you can use the DSIG package. This one, we have to use a complete different data set. So far, what we use is peak intensity one. So for count data, forget about what we are done so far. Let's read the new data sets. So there are IPRG count data in that folder. So let's read this data set. In this data set have a completely different shape. If you can find the ABRF paper in the supplementary information, they have a link for FTP to get all the raw file and then all the intermediate process data set. And this is the one of the data set for count, spectral count. So basically, if they found any specific peak, they just mention it. So first, what we need to do, we need to make a count table. How many spectral count we have that specific run and that specific proteins. Okay, so this is the one of the examples. So this is from the IPRG count data, that specific proteins and that specific run. Here it shows 1, 2, 3, 4, 5, 6 different rows. Means they have a 6 spectrums over there, right? So we need to make this, we actually make this count table, use this dcast one. This one is also to make by protein, by run, if they don't have any variance. We did not set what kind of variable you want. Basically, they just count the number of the rows, the specific cells. So if you run this, here it says aggregation function is missing. They don't know what they have to do this. So default, they use the length. They basically count how many rows they have and then run. Now we have this type of the data. So for each protein, for each specific run, how many spectral count they have. Okay. This is also wide format, so we can ready to use this one. So we need to get only this number part, and then we want to save this protein ID separately. So this is what I did. So from here, I want to remove first column and then keep the rest of the information. And then I will call this is count data. And if I check the how count data look like, here, they only take only number part. Count data. And the protein name variable, I will get only protein IDs. So if I run this, and here I have only the protein names. Okay. Then let's call dsig package. Okay. Across everything, MSD, Lima, dsig, always, they don't know about each column came from which conditions. So always we need to set some design metrics which annotate each run came from which specific conditions. So here it is. So I just want to make a similar table as what we made for the Lima. And let's check how it look like. So similar tables, right? Each row means column information, and then this specific column came from which conditions. So first column should be the condition 1, and then here, for example, 10th column should be condition 4. Okay. And then similar as Lima, we need to say, okay, here is the designer matrix, and then we have a data count and what kind of comparison I want. We need to set it. So before, the Lima has a make matrix function, but here dsig data set from matrix functions. So basically they also make a matrix depending on their design and what kind of comparison do you want. And here you need to put your count data and then group information, exactly your design. And then you need to say, then what kind of comparison I want. They assume the first condition 1 as a reference. This tilt means verse what the others. So in this case, condition 1 versus condition 2, and condition 1 versus condition 3, condition 1 versus condition 4, and so on. Okay. If I run here, let's check what this output for this analysis have. It looks quite arbitrary. They have inside, they have some value, but they print only some of the options. And then let's check what the result name has. It looks also quite weird. Then we need to get some their result information. So for example, first, condition 1, condition versus 2, this is what we set, and so on. So basically for 3 different comparison, we can extract their information. Okay. Yes. And then there are also a little bit complicated the reformatting one to get some to make like nice format. So here I just a little bit make a different order and so on. Now we have the result table for count. So here they also have for each protein, for each specific comparison, how much log2/4 changes they have, how much the standard statistic p-value, and then the adjusted p-value. This one also for the Benjamin Hoffman one, the same adjusting method. And then I will just a little bit change the order. So here I just want to make the protein first and level and so on. So here just make a different order of the column. And now protein go first and so on. It will be similar as what we saw. And then just change the column name. And then I just save this one in the same folder. So in the data skyline file, you already have this result one. So that one is only for 3 comparison, 2 versus 1, 3 versus 1, 4 versus 1. And then I already generate for the other groups, and then here is the result. So test count DSEQ result all include all the result from DSEQ analysis. So if you click that R file from the folder, it says the compound rolled R data, yes, and then it will automatically load out my result over there, and then you can check their results is there, and then also can check there are total 6 different comparison are there. Okay. So you can compare this one with what we practiced yesterday and then Lima too, right? Because yesterday we used the peak intensity one. Here we use the spectral count one. So if you want to draw that one also, you can draw the volcano plot. But here, let's assume we have a 2 result, and then you want to compare how much is difference. So let's call here in the same folder, skyline result is what we got from yesterday. Okay. So here skyline result is the result from yesterday what we practiced, and then here test count, this long name one is from spectral count one, right? Now we can compare how many significant protein and comparison we have. So ideally we have 36 comparison we have, because we have a 6 proteins, spiking protein, and each one have a 6 different comparison. So totally ideally we have to find the 36 one, right? Then let's check it. From skyline result, based on adjusted p-value, let's apply their cutoff 0.05, and then they can get subset of only significant comparison and proteins. So from skyline result, if the adjusted p-value is less than 0.05, we just make this is another data set. And then let's check their dimensions. There are 29 rows and 11 columns. The column, we don't need to worry about this, but the number of the rows shows the comparison with have adjusted p-value is less than 0.5, right? So let's check how it look like. Head, skyline, MSDSEQ. Here, if you look at the adjusted p-value column, it should have the less than 0.05. Among this 29 row, let's check how many unique protein we have. So from this subset of data, let's check the unique protein ID. And then it shows 6 different proteins, but we spike only 6 ones. But here, this, only 1 protein, which have to be background, which should have not significant, but we can see this is probably they have a false positive one. Okay. I will repeat the same thing for this spectral count data set. It looks long because my data name is really long, but however, it's the same thing. From here, I'll just p-value is less than 0.05. And then now we have a 25 only. So we have 4 less number of the comparison. And then let's check among them. Let's check how many unique protein ID they have. Okay, this should be capital. 1, 2, 3, 4, 5, 6. 6, and then every protein ID is exactly what we spike in, right? However, we found the last number of the total comparison, significant comparisons, and so on. So this is just a brief idea how you can get it and then subtract and then look at more detailed one. If you want to compare estimate for itself, you can see head, skyline, significant one. It shows a log 4 changes here. I want to check count DC, head. You can compare these 4 changes. For example, here, first row is for P44374 protein and then 2 minus 1 comparison. And this is the log 4 changes. And here, it's the same thing. You can see they have different log 4 changes and so on. Here, let's compare this one. 449A3 proteins. Let's go back to our design tables. 449A3, 2 minus 1 is a 65 versus 2. Then, if you can calculate it, log 2 divided by 2, it should log 2 4 changes around 5. And here for skyline, the peak intensity one, they have a 6.1. Here they have a 4 point something. It's a little bit less than this one, right? And then let's check the P55249. Check 5 here, 2 versus 1, 10 versus 500. What is the correct 4 changes? Log 2, 500 divided by 10. It should be 5.64. And then here is this much. And here is just only 3, right? So I just compare their estimate for changes itself for spectral count versus intensity one. If you go to the ABR paper, one of the figures show their estimate for changes, how much is difference. Spectral count data set, commonly they can underestimate for estimate for changes versus the peak intensity one is quite relatively, it's a better estimate log 2 4 changes and so on. Okay, so this is quite overview what we can do so far. So do you have any question about this analysis one? Yeah, so that is this one for MS-DET one, we can assign the 2 first and 1, but here is always 1 is the reference minus something, so it should be completely opposite way. This is how I label it, but it's actually it should be 1 minus 2, C1 minus C2. That's the reason they have a completely opposite sign, this result versus this result. Okay. All right, so we have a 5 minutes left, but we had less break before, so we can get more break this one. And if you have any questions, let me know. I will work around that one. Yes.
Yeah, but that means you have to install it. It's a file converter package. So you gotta change the file converter. You have to change the package. Yeah, you have to do it manually. If you go back to your console. If you run the script. They emailed it out a few days ago. They said the script's not working. It just runs like program class.